So if your depositions during additive manufacturing, especially titanium alloys when you are making, this huge difference you will get. If you vary laser power to a smaller extent, suddenly green lines will increase. Or if you increase, red lines will increase. With minor fraction, say 5% to 8% variation in red line increase, will sacrifice the problem. What extent the sacrifice? Not just 10 megapascal, 15 megapascal. It is like say 500 to 300 will come down. So it's not that major chemistry is varying, not new phases have found. If conventional microstructure, you say nothing is there, no change. Between two parameters, same microstructural features, but properties totally different. What is the culprit? This must be known to us. Otherwise, the question mark remains question mark. So that's what I am saying, that characterization tools plenty are available. Which tool can solve our problem? We have to address it. Yeah, this is melted vertical column, the deposition column grade orientation we have made, and related again boundary distribution. First one, if I build like this on the top surface. Second slide say on the wall side, build direction, center direction. Huge variation, significant variation. This is the reason for having wide variation of mechanical properties in different directions of the additive manufacturing. Build direction and normal to build direction. This many images I am showing, this many times we will not do it. One scan we will do it, that's it. No, EBS. Of course, that is also diffraction, this is also diffraction. This is an attachment to SEM. Run one scan, you will get 16 such kind of maps. Each map will give very insightful information. In fact, EBS will become very powerful tool nowadays that one scan you do it. You can write something like 7-8 pages on that one because that much information is there. This fellow is kernel average disorientation maps we used to call. The color variation will give you strain variations. In fact, it is also called as a micro strain map. One color variation in the sense that color to adjacent color, that much localized strain variation is there. So you can understand at the grain boundary, adjacent to the grain boundary, how much strain variation is there. Second phase is there. At the second phase, at the interface, and first phase, what is the strain variation? All this information you can get comfortably from this CAM map. This you will not get additionally. One scan you run, post-processing software is there. In that you put your data, whatever you want you can. All you want 16 apps you will get. But what is useful to you? That is going to be a key part. I am saying characterization tools are plenty. Every tool will give numerous information which is useful to you. Is a challenge from you that you have to pick appropriately. I said the hatching. People may think that what is there, instead of depositing like this, I will deposit like this, or I will deposit like this. So the property variations are abnormally there, not in a small levels. And this is with respect to conventional property. Orientation based property is, in fact, on table I did keep for titanium 67418. In build direction, you will get 1500 megapascal. In transverse direction, sometimes you will get 320 megapascal. 1/5. That means build in this direction, put component in another direction, it will fail. It is inferior than your rod system. Commercially available titanium also much better than the other direction. So orientation is much crucial, build direction is much crucial. For that, some verifications of tensile properties we have done and we have evaluated. Even in basic internal work hardening behavior also totally changed. To a great extent actually. Yeah. When you combine the information of whatever I have mentioned, you will see like this. You can see where strains are more. whether in that location disorientation angles are more or dislocations are more, or low angle boundaries are more or stacking faults are more. All the information in one nutshell you will get. This also you can use it. Which is hard spot or which is weaker section, where the damage can initiate. Yes, you can use it. This is defect free, physically defect free system I am saying. If porosity is there, that is default defect free domain. This is for orientation analysis we have done by selecting one grain, and that grain when it is getting deformed, what is shape change, what is strain module variations, all things we have calculated. That's not now much necessary, but it is possible. Every tiny aspect we can get into the picture. The next one is high entropy alloy. It became a very big challenge. Then we have taken first one. We want to see first its basic nature. We have first done vacuum arithmetic, rod system. Become like a button. We have hammered. It's slightly reduced. Then it is very soft. So I told my student, okay, reduce it to say 1 mm thickness and bring it to 1. That fellow disappeared. After 2 weeks he came. Sir, I am not able to thin it down. I want to put it on railway track. He said. That was not thin below 5 millimeters. He went to blacksmith, hammer, everything he has done. Anvil got broken, he was charged 5,000 rupees for that one. Okay. Why I am saying this thing is, high entropy alloys are such a wonderful work hardening material. First hammering is good, latest hammering is difficult, third level hammering is impossible, even hammer can break. Such a kind of, why high entropy alloys are becoming popular, I am just giving one example. Such material, such a cocktail material, for building in SL, it became a very big challenge. We built it in Estonia, in Europe, in one of my friends' lab. For optimizing these parameters, almost 1.5 years. 1.5 years. When depositing itself, crack used to come backside. First level. When we are depositing, it used to split. Hell lot of nonsense problems we have faced. Finally, we have optimized. We got it 99.7% density. He spent there for 1.5 years, my first student in Estonia, to optimize this one. Optimize, later published 13-14 papers, that is different. But after optimizing, we felt very much fascinating and interesting results from this one. So this is how the optimization was done. All these things are optical micrographs. Then scanning electron microstructures and its elementary distribution. Along the build direction, elements used to segregate. High entropy alloy concept is A atom is there, which will be surrounded by B, C, D, E. B should be A, C, D, E. Like that it should be there. Then only it is ideal distributed. If A are getting segregated, in other locations A population will come down. Then that high entropy effect will come down. Especially when doing selective laser method, we felt that complete channel, element used to separate. That is the reason we can crack everything. Even after optimizing and getting physically defect-free system, metallurgical defects used to stay. And these things when we have analyzed, we realized that they are detrimental phase. Detrimental phase actually there is. That means in application when you keep it, it will fail. We realized that we have taken one sample and tested with 10 megapascal test tube, which is supposed to give 2000 megapascal with 10 megapascal test tube. Our doubt is correct. When we have done crackographic analysis and other things, clearly it has demonstrated this base phase it has evolved as a result of selective laser welding is a culprit that we have learned. Then again we have started from scratch. Again analyzing all these things. There are parameters like laser head shaking or bed shaking techniques we used to adopt. Thereby we used to create a breakdown of this elemental distribution, and finally we have optimized it. That's why it took almost like 1.5 years or so. XRD confirmed, yes, it is perfect SCC structure with the latest parameter variation, very gradual, with a wonderful strain distribution pattern from XRD. I told you XRD can give you lots many information from one scan again. Then anisotropy character when I want to evaluate, you need to go to high-end techniques from starting from optical. You can take all phases, you can do this microstructure analysis, you can get this. Quite good information, very interesting information you have. Then we have done this anisotropy using the EBSD analysis. So anisotropy is still at a higher level, but it is within the acceptable level, which is equivalent to other informal sound like this is the elemental distribution map and other things. Transmission electron microstructures has revealed a wonderful dislocation cell structure with very beautiful night modes, defect-free, and uniform arrangements of dislocations. Normally, people will talk about dislocations, stacking faults, this, that kind of things more, but which you can see practically using transmission electron microscope in lattice resolution imaging like this. It's not a difficult thing. Any TEM operator, if you request more than 200 keV, you can get this kind of images. If operator is very comfortably, you can calculate what is streaming, what is nanospeed, what is stacking fault, everything you can easily estimate. Their population in the respective direction can give us whether the property can be improved or not. To confirm this, what phase it is at that locations in this high entropy line, normally high entropy line phase maps and other things will not be available. There is a software called CalPad, the explanation software. Using CalPad